Hello and welcome to GCA Masters TV and you're watching Saturday Night Live. Tonight, we are going to have a look at a tile and touch upon its various interesting old and new developments and those associated with tiling patterns. According to Dr. Katie Spaulding's article on IFL Science, thanks to non-professional mathematician David Smith, along with a team of academic researchers hailing from across the UK and US, this brand new Einstein-tile can do something no other shape can do. That is, his hat-shaped polygon can cover an infinite space and never once repeat itself. There's no relation to the famous physicist. In this case, Einstein comes from the German Einstein, meaning one stone, and it's a pretty apt name for the special little shape. That's because the hat can do something no other known shape can. It tessellate with itself in such a way that it can cover an infinite surface without ever creating a repeating pattern. Even knowing that it does, the solution has turned out to be disarmingly simple. Although the paper has yet to be peer-reviewed, experts believe it's likely to hold up to scrutiny. Finding the tile, and proving its aperiodicity, required the us of both powerful computers and human creativity. Goodman Strauss told New Scientist, "You're literally looking for like a one in a million thing. You filter out the 999,999 of the boring ones, then you've got something that's weird, and then that's worth further exploration," he explained. Aperiodic tilings are important in the development of quasicrystals, which in turn have found applications in everything from Kleenexes to real-life Terminator-style robots. For some, though, the potential uses of the admittedly cute new shape start closer to home, that is in architecture and interior design. So what is a definition of a tile? A tile is a flat, usually square or rectangular piece of material such as ceramic, stone, or glass that is used to cover surfaces like walls, floors, and roofs. Traditional tiling involves using tiles of a single shape and size that are arranged in a repetitive pattern to cover a surface. While this method of tiling has been widely used for centuries, it can lead to a monotonous and predictable design. Furthermore, traditional tiling often requires a large amount of cutting and waste, as tiles need to be cut to fit irregularly shaped spaces. This can be time-consuming and costly. Additionally, traditional tiling can be difficult to install and maintain, as it requires a high degree of precision and attention to detail to ensure that each tile is aligned and spaced correctly. In graphics, a tile pattern refers to the arrangement of small images or shapes, called tiles, into a larger design or pattern. The goal of creating a tile pattern is to produce a seamless or repeating pattern that can be used to fill a large area without visible seams or discontinuities. Tile patterns are commonly used in digital design, including web design, game design, and 3D modeling, and can be created using various tools and software, such as Adobe Photoshop, Illustrator, or dedicated tiling software. They can be used for backgrounds, textures, and other design elements. The problem with traditional tiling patterns is that they can be boring and predictable. When used in interior design and architecture, they can create a monotonous and uninteresting visual effect. This is especially true when traditional tiling patterns are used in large spaces, such as hotel lobbies or office buildings, where the lack of visual interest can make the space feel uninviting or sterile. In addition, traditional tiling patterns can also limit the design possibilities in interior design and architecture. For example, if a designer wants to create a unique or complex pattern, they may be limited by the traditional tiling patterns available. However, with the advancement of technology, new tile materials and digital design tools have allowed for more innovative and customizable tiling patterns. This has opened up a world of possibilities for interior designers and architects to create more unique and visually appealing spaces. Here are many examples of exciting tiling designs that, like Penrose tiles, have unique and intricate patterns that do not repeat. Here are a few. Ammann-Beenke tiling. This tiling is another example of an aperiodic tiling, meaning that the pattern does not repeat. The Ammann-Beenke tiling is made up of two types of rhombus shapes, which are arranged in a way that creates a complex, maze-like pattern. Wang tiles. These are square tiles with colored edges, which can be arranged in different ways to create a pattern that does not repeat. The edges of each tile must match the adjacent tiles, so that the pattern remains coherent. Conway's Game of Life. This is a computer simulation of cells that live and die according to certain rules. When the simulation is run on a grid of squares, certain patterns emerge that can be used to create intricate undetailed designs. Escher tiles. These tiles are inspired by the work of the artist M.C. Escher, who was known for his intricate and impossible designs. The tiles can be arranged in different ways to create a pattern that appears to be three-dimensional, but is actually flat. Quasicrystals. These are materials that have a unique atomic structure, which results in a pattern that does not repeat. Quasicrystals were first discovered in the 1980s and have since been found in a variety of materials, including metals and ceramics. Each of these tiling designs has its own unique properties and applications, from computer simulations to architectural design. They demonstrate the incredible diversity and creativity of mathematical patterns and designs. Now let us take an example of Penrose tiles. Penrose tiles are a set of two-dimensional shapes that can be combined in an infinite number of ways to form patterns that do not repeat. These tiles were first discovered by Sir Roger Penrose in the 1970s and have since become an area of interest for mathematicians, artists, and designers alike. The unique properties of Penrose tiles have made them a fascinating subject for research in the fields of mathematics, physics, and materials science. Penrose tiles are named after their discoverer, Sir Roger Penrose, who is a renowned British mathematician and physicist. Penrose discovered these tiles while exploring the properties of non-periodic tilings, which are patterns that do not repeat in a regular way. Unlike regular tilings, which use a single shape repeated to create a pattern, Penrose tiles use two shapes, a rhombus and a kite, which can be combined in a variety of ways to create intricate patterns. One of the most interesting properties of Penrose tiles is their ability to create patterns that appear to have an infinite level of detail. These patterns can be seen as fractals, which are geometric shapes that have the same level of detail at every scale. This property has made Penrose tiles useful in the study of fractal geometry and in the design of materials with specific properties. Penrose tiles have also been used in the field of quasicrystals, which are materials that have a unique atomic structure that is neither completely ordered nor completely disordered. The structure of quasicrystals is similar to the structure of Penrose tiles, and they have been found in a number of different materials, including metals, ceramics, and even some biological molecules. In addition to their scientific applications, Penrose tiles have also become popular in the world of art and design. The intricate patterns created by these tiles have inspired a number of artists and designers, who have used them to create everything from jewelry to textiles. Penrose tiles have even been used as the basis for building designs, such as the Penrose tiling on the facade of the Mathematical Institute at the University of Oxford. In conclusion, Penrose tiles are a fascinating mathematical discovery that has found applications in a wide range of fields, including mathematics, physics, materials science, and art and design. The intricate patterns created by these tiles have captivated scientists, artists, and designers alike, and their unique properties continue to be the subject of ongoing research and exploration. Tiling patterns have a wide range of applications across various fields apart from building design. Some of the common applications are textile design. Tiling patterns are used in textile design to create repeating patterns on fabrics such as wallpaper, clothing, and upholstery. Computer graphics and animation. Tiling patterns are used extensively in computer graphics and animation to create repeating textures and patterns on surfaces such as walls, floors, and backgrounds. Mathematics and geometry. Tiling patterns are used in the study of mathematics and geometry, particularly in the fields of crystallography and group theory. Cryptography. Tiling patterns can be used in cryptography to create secret codes and ciphers that are difficult to break. Art and decoration. Tiling patterns are used in art and decoration, particularly in the creation of mosaics, stained glass windows, and other decorative surfaces. Gaming and puzzles. Tiling patterns are used in games and puzzles, particularly in the creation of jigsaw puzzles and tile matching games. Industrial design. Tiling patterns are used in industrial design to create textured surfaces on products such as flooring, wall panels, and packaging. Dan Shechtman was an Israeli scientist who was awarded the Nobel Prize in Chemistry in 2011 for his discovery of quasicrystals. Shechtman's work challenged the established scientific beliefs about crystals and revolutionized the field of materials science. In the early 1980s, Shechtman was studying the structure of metal alloys using electron microscopy. He observed a pattern of spots on the images that did not fit the typical symmetrical patterns of crystals. Shechtman's discovery of quasicrystals, which have a non-repeating pattern of atoms, went against the prevailing scientific belief that all crystals had a repeating pattern. His colleagues and even his mentor, the renowned crystallographer Linus Pauling, dismissed Shechtman's findings as impossible and garbage. Shechtman persisted in his research and collaborated with colleagues to further investigate quasicrystals. They found that quasicrystals have unique physical properties, such as low friction, high hardness, and thermal insulation, making them useful for a variety of applications in industry, such as coatings, alloys, and insulating materials. Shechtman's discovery was eventually accepted by the scientific community, and he was awarded the Nobel Prize in Chemistry in 2011. Shechtman's work has opened up new avenues of research in the field of materials science and has led to the development of new materials with unique properties. Shechtman's story is a reminder of the importance of perseverance in scientific research and the need to challenge established beliefs. His discovery of quasicrystals has paved the way for new discoveries in the field of materials science and has had a significant impact on technology and industry. So how can discovery of non-repeating tiling pattern can revolutionize various fields in coming times? The discovery of non-repeating tiling patterns, such as the Penrose tiling, has the potential to revolutionize various fields in the coming times. One of the key areas where this discovery can have a significant impact is in materials science. Traditional tiling patterns, which involve repeating units, limit the properties of the material they are used to create. However, non-repeating tiling patterns have the potential to create materials with unique and interesting properties. For example, non-repeating tiling patterns can be used to create materials with better strength-to-weight ratios or better electrical conductivity. Non-repeating tiling patterns also have the potential to revolutionize the field of architecture and design. Traditionally, tiling patterns have been used in architecture and design for decorative purposes. However, non-repeating tiling patterns can be used to create structures with unique and interesting shapes that are not possible with traditional tiling patterns. This can result in more efficient use of space, more aesthetically pleasing designs, and even better acoustics in buildings. In addition, non-repeating tiling patterns can also have applications in computer science and information theory. The discovery of non-repeating tiling patterns has already led to the development of new algorithms for generating and analyzing tiling patterns, which could have implications for computer graphics and image processing. Overall, the discovery of non-repeating tiling patterns has the potential to revolutionize various fields in the coming times. That brings us to the end of the episode. Please click on the bell icon below to subscribe to our channel. It will help us immensely to bring to you more and more interesting content. See you next week.